Hello, Namaste, Konnichiwa, welcome to Sunny Sensei. In this lesson, we will understand the relationship between the zeros of a polynomial and its coefficients. But before we begin, let's do a quick recap. So, what do we mean by a zero of a polynomial? A zero of a polynomial, p of x, is a value of x for which the polynomial becomes zero. And graphically, it is the point where the graph of a polynomial meets the x-axis. In this plot, these are the two zeros of this polynomial, the points where the graph meets the x-axis and where the value of the polynomial is 0. Now here is something interesting. What if I tell you that we can predict the zeros just by looking at the coefficients of a polynomial? Let me explain this with a simple polynomial. P of x equals 2x plus 4. The highest power of x is 1. So this is a linear polynomial. Now, the general form of any linear polynomial is ax plus b. In our example, the coefficient a is 2 and the coefficient b is 4. Let's now find the zeros of this polynomial. We start by equating p of x to 0. 2x plus 4 equals 0. 2x equals minus 4. And x equals minus 4 over 2. That is minus 2. So we have a 0 at x equal to minus 2. Let's call this 0 alpha. Alpha equals minus 2. Now observe this carefully. The 0 is minus 4 over 2. Both 4 and 2 are coefficients of this polynomial. Let's understand this further using the general form of the linear polynomial, ax plus b. As before, we find the 0 by equating p of x to 0. Ax plus b equals 0. That is, ax equals minus b, or x equals minus b over a. Notice that the 0 depends only on the coefficients a and b. So, for a linear polynomial, the 0, alpha, equals minus b over a. Let us now see what happens in the case of a quadratic polynomial. Here is our example. 2x squared minus 7x plus 3. This is a quadratic polynomial of degree 2. Now, the general form of any quadratic polynomial is ax squared plus bx plus c. In our example, a is 2, b is minus 7, and c is 3. Now to find zeros of our example polynomial, we equate p of x to 0. 2x squared minus 7x plus 3 equals 0. To factor this, we rewrite the equation as 2x squared minus 6x minus x plus 3 equals 0. From the first two terms, we factor out 2x. So we have 2x, x minus 3. From the last two terms, we factor out minus 1 and we get minus x minus 3. And this equals 0. Now we factor out x minus 3 and we have 2x minus 1. X minus 3 equals 0. So the zeros are x equals 1 over 2 and 3. Let's call these two zeros alpha and beta. Alpha is 1 by 2 and beta is 3. Now we have the zeros, but can we relate these zeros to the coefficients of the polynomial? Let's understand this using the general form of a quadratic polynomial. P of x equals ax square plus bx plus c. Now since alpha and beta are the zeros of this polynomial, we can write this polynomial as k x minus alpha, x minus beta. Notice that for x equal to alpha and for x equal to beta, the value of polynomial is 0. We also need the factor k to account for the coefficient of x square. You will understand this better as we move ahead in this lesson. We have ax square plus bx plus c equals k x square minus alpha x minus beta x plus alpha beta, or kx square minus k alpha plus beta times x plus k alpha beta. Now we compare the coefficients on both sides of the equation. These coefficients must be equal. So we have a equals k, the coefficient of x. B equals minus k alpha plus beta, or alpha plus beta equals minus b over k. Now k equals a. So alpha plus beta equals minus b over a. Now the constant term c equals k times alpha beta, or alpha times beta equals c over k. Again, we replace k with a and we get alpha times beta equals c over a. These two results establish the relationship between the zeros and the coefficients of a quadratic polynomial. The sum of zeros, alpha plus beta, equals minus b over a. The product of zeros, alpha times beta, equals c over a. Now let's verify these results using our example. The coefficients a is 2, b is minus 7, and c is 3. And the zeros are alpha 1 over 2 and beta 3. Now starting with the sum of zeros. On the left hand side, alpha plus beta equals 1 over 2 plus 3, which gives us 7 over 2. On the right hand side, minus b over a becomes minus 7 over 2, which is again 7 over 2. So the left hand side equals the right hand side. Next, we have the product of zeros. The left hand side is alpha times beta, which equals 1 over 2 times 3, or 3 over 2. On the right hand side, c over a is also 3 over 2. Once again, the left-hand side equals the right-hand side. So, the relationship that we derived works perfectly for this polynomial. Let us now move to a cubic polynomial. P of x equals ax to the power 3 plus bx to the power 2 plus cx plus d. Let's assume that the zeros of this polynomial are alpha, beta, and gamma. Just like the quadratic case, we can write the polynomial as k, x minus alpha, x minus beta, x minus gamma. Now we can expand the right-hand side to get next, we compare the coefficients on both sides. And this gives us three equations relating the zeros and the coefficients. First, the sum of zeros. Alpha plus beta plus gamma is minus b over a. Second, the sum of pairwise products of zeros. Alpha times beta plus beta times gamma plus gamma times alpha equals c over a. And finally, the product of zeros. Alpha times beta times gamma equals minus d over a. Just like the linear and the quadratic polynomials, cubic polynomials also have a relationship between the zeros and the coefficients. Let me now summarize everything that we have learned in this lesson. As the degree of the polynomial increases from linear to quadratic to cubic polynomials, we see a clear pattern. The relationship between the zeros and the coefficients becomes more and more complex, but the core idea remains the same. The zeros of a polynomial are closely related to its coefficients. With this, we come to the end of this lesson. In the next lesson, we'll solve some important board exam questions on polynomials. If you enjoyed this lesson, don't forget to like, share and subscribe to Sensei. Thank you and see you again soon.